Okay, next let's take this simple model of energy balance to the next step by taking it as a equation that is still evolving in time. We found solutions by looking for equilibrium and setting this to 0. So looking at our equation again, the time rate of change of our simple one layer atmosphere was a balance of the incoming short wave and outgoing long wave, where we had introduced emissivity of the surface, so the surface was not a black body but a gray body, and that gave us a solution that we already looked at, and we introduced one layer as we did before in the energy balance in the earlier part of the course. Let's now look at this as an example of how numerical solutions are developed, and we do that by starting with the assumption that the temperature T here is a function of time. So we are still dealing with averaged situation where we are not zero dimensional anymore, we are evolving in time. So time is one dimension, and that is a function of some mean climatology, let's say T bar, plus some deviation from the climatology, which is also dependent on time. Climatology basically means it's fixed over the time of integration we are looking at, and of course there is no reason why this would be fixed when you go for longer time periods. How long? Well, typically we say climatology is 30 years, but this is quite arbitrary. But definitely when you go from the industrial beginning of the industrial revolution to now, we have often used baselines like 1961 to 1990, 20th century and so on, to look at deviations from those. We are not necessarily saying those are climatologies, we're just saying those are the base periods around which we are computing climatologies. So that amounts to the same thing, except here the assumption is that this T tilde anomaly is much smaller than T bar, which allows us to write numerical relations, as we will see in a minute. So T bar is constant, it's not dependent on time, so when you plug this into here, the dt bar dt term drops out, so you end up by cancelling out the pi r squared terms and taking the 4 on this side, we end up with h rho c times d tilde dt tilde dt, so time evolution of the anomaly around the climatology, equal to 1 minus alpha divided by 4, which is coming from here, times S0, pi r squared is cancelled, minus, so 4 pi r squared is cancelled, minus epsilon sigma, and now we are writing T as T bar plus T tilde to the 4th using this expression here. So now we can write this based on the fact that T tilde is expected to be much smaller than T bar. We can expand that. So first write it as T to the 4th times 1 minus 1 plus T tilde or T bar to the 4th. So that's fairly straightforward. You take it out and then use Taylor series expansion on this, because here T tilde divided by T bar is much smaller than 1, and that allows us to use the mathematical construct of series expansion of such a exponential, such a term. Okay, so 1 plus x to the n in a Taylor series expansion looks like 1 plus mx plus n times n minus 1 over 2x squared plus higher order terms. And you've probably seen this somewhere. So the more the term you add, the closer you are going to get to the actual value of 1 plus x over to the n. And of course the idea of numerical solutions is that you want to simplify this by making some assumption about how many terms you want to keep, to what order the terms are important. So with x equals to T tilde or T bar then, and n equal 4, neglecting the higher order terms in this expansion, with regard to t tilde being much smaller than t bar, we obtain from this equation and this one here, sorry, 2.2, which I didn't include here, but you know what that is. Let's see, we can go back to 2.2. This is our 2.2, which is an analytical solution for equilibrium we found for the temperature. So obviously that's the long-term climatology, because that's what equilibrium temperature is, that we are representing here as T bar. Okay, T bar is the same as looking for equilibrium solution by setting the left hand side to 0, and the deviations from that are written this way. So we are still doing the expansion. So d tilde bar dt, anomaly evolution, then is equal to minus this expression for epsilon sigma t bar to the cube divided by h rho c times t tilde. This is a linear equation because there is no multiplication of t bar with itself, and it's first order, and it's linear, as I already said. And those who know a little bit of math of ordinary differential equations know that we can take this one here and take dt over here and integrate both sides, and whenever you have an expression like dt tilde divided by t tilde, you end up with an exponential solution. So t tilde as a function of time then just becomes equal to constant multiplied by exponential minus t divided by tau, where tau is now the term we are summarizing into. So height of the globally averaged atmosphere we are looking at times air density times its air heat capacity divided by emissivity of the surface, Stefan-Boltzmann constant, and cube of the long-term average or equilibrium temperature. This, if you do the numbers, turns out to be dimension of time, which is the characteristic time of the system. In other words, T bar is to remain constant here. Then if you somehow perturb and produce an anomaly T tilde, which is a function of time, let's say you had a burst of solar energy or a volcanic eruption or emissions from human beings or whatever, then how quickly will the system return to T bar? That's the characteristic time, tau, and in our case here it turns out to be about 35 days. So in our simple solution, the radiative equilibrium says that if we perturbed the temperature from its equilibrium temperature, within about 35 days it's going to get back to the equilibrium temperature. So what are we going to do then? We are trying to write the numerical solution where we can keep on predicting these temperatures. So here temperature time t, time t can be split into n steps. So if you want to get to tomorrow, when you integrate numerically, you will take a time step during this numerical integration as 1 hour, 6 hours, and so on. These are the time steps of integration because now we are numerically integrating. Okay, we will see what that means in a minute. So there are n time steps to go forward, with each time step being delta t. And I will just say some things that if you understand, fine. Otherwise, if you are not interested in numerical modeling, don't worry about it. If you are, then obviously you'll have to learn much more about this. Delta t is a time step, so it's the time step at which you will move your numerical solution forward. Either you can do it by hand if it's simple enough, or you need a computer, which is why all computer models, all climate models are done on computer because it's too complicated. But for learning purposes, this is how we do it. So if n is 0, then it's the initial value of t tilde at time 0, and then n equal 1 is time step, 1 time step, then 2 time steps, and so on. So here any temperature t at time t plus delta t can be written as the value at time t typically that's the initial value, plus the time rate of change of temperature times one time step plus 1 over 2 factorial d squared t dt squared second derivative acceleration term in a motion sense times delta t squared. So this is again the Taylor expansion. So as you drive delta t towards 0, you are going to basically get exact solution, right? That's how derivatives are done. When we say dt dt, it's basically delta t divided by delta t, delta temperature divided by delta time, with delta time tending towards 0, right? Remember your basic math. So now write this as dt dt. So we're trying to find an expression for time rate of change of temperature. So you take this side, t temperature times t plus delta t minus tt divided by delta t, minus this, minus that, and so on. So this is the approximate expression for time rate of change of temperature, and these are the terms of order delta t and higher. So this is time delta t squared, and so on. So if you decide that you are going to ignore these terms, then you are going to estimate the time derivative of temperature with this expression, with this representing the order of accuracy. That's how much you have ignored. Okay, so you can also write it as the second. So you can write a similar expression for temperature at t minus delta t. So it will become tt minus dt dt delta t, and so on. And you can add the two or subtract the two and get a second order expression for time derivative of temperature, which will look like t times t at t plus delta t minus t at t minus delta t. So you are at this time, you are taking a value at the next time step, future time step, and a past time step to estimate the time rate of change at the current time step. So here it's 2 delta t. You can just write the expression and make sure you get it right. Now this first, or the first term here is order delta t squared, and the second one is order delta t to the fourth, whereas here the first term was order delta t and the second term was order delta t squared. So those are the terms you end up neglecting. So this is second order accurate, this is first order accurate, which means if you take a large delta t, the potential error you make in your numerical estimation of dt dt is going to be order first order delta t, of course multiplied by this. So that's how numerical methods work. That's a very quick introduction, but this is an introductory course. So you can find references where we typically write numerical expressions for derivatives. F prime x is df dx. It's the first order finite difference. Error is of order delta x, delta t, delta y, delta z. Everything is going to look similar, whether it's time or space. So this is called Euler forward method, when you write the same thing with a previous value or the value in longitude behind versus forward. Then you get Euler backward scheme. They're called schemes, numerical schemes, numerical representations. F prime x can be written as order delta x squared as a centered difference that we just looked at. So f x plus delta x minus f x minus delta x divided by 2 delta x. Then second derivative similarly follows an expression like this, which is order delta x squared. This is second centered difference for a second derivative. So when we look at climate equations, we will see that there are first order terms, second order terms, or first derivatives, second derivatives, third derivatives, and so on. And that's how we solve them, by approximating the derivatives in these numerical ways. There are many issues involved there as to how you choose which scheme is the best. uh, infinite considerations about the stability of the numerical integration, things like maintaining positive values. For example, if you're integrating an equation for humidity or mass cannot become negative, humidity cannot become negative, so your numerical method has to make sure that it doesn't produce errors leading to negative mass or negative humidity and so on and so forth. Okay, so let's look at an example with the continuous. Maybe I'll stop this and do this in the next podcast because it's already 15 minutes. So we'll look at a equation and look at some numerical solutions and try to explain a few more details. But numerical solution of a first order linear differential equation, we showed how derivatives can be approximated numerically using Taylor series expansions, Euler forward, Euler backward, center differences, and so on. Okay.